Hi, and welcome to Lesson 8.4. Yesterday we looked at a confidence interval for the difference between two proportions. Today we're going to be looking at the significant test for the same statistic. And you know from previous work that the significance tests and the confidence intervals are kind of like hand in glove, okay? They do sort of the same thing, except the confidence interval predicts what the population proportion will be based on the mathematics, and the hypothesis test decides whether or not the population parameter is what you think it is, okay, based on mathematical analysis. So they kind of go together. When we looked at the confidence interval, we were looking at the size of the difference between two proportions. Today the size of the difference isn't the deal. It's whether that difference is statistically significant. The null hypothesis in this type of test, the difference of two proportions, is always the same. Your null hypothesis will be that the two proportions P1 and P2 are equal. Now, if you wanted, you could say that same thing by saying that the difference between them, P1 minus P2, would be 0. It's up to you which way you phrase it. I happen to like this because this is more, it's in keeping with that idea of comparison. So I like this one better. The alternate hypothesis can take three forms, and that's not any different than we've used before. We can either have P1 less than P2, P1 not equal to P2, or P1 greater than P2. Less than, not equal to, greater. Those are always the same for us, the same three choices for the alternate hypothesis. The general form of a test statistic is always the same thing, folks. It is a z-score, and that is the sample stat minus the population parameter divided by the standard error of the sample stat. Now we have to fit our stuff in here, our variables with p-hats and such, and that's what we got to think about next. For this particular sample statistic, we pool the two standard errors together, and we do it following this format. It is the standard, or it's the square root of, and under the radical, a p-hat, notice that there's no number on here, and a q-hat with no number, okay, multiplied by 1 over the first sample size plus 1 over the second sample size. Folks, p-hat with no number there, it's a pooling of the probability. That is, p-hat in that formula is equal to p-hat 1 plus p-hat 2, you add them together, the number of successes, over the total sample size. Okay, it's a pooling again. You're averaging out the proportion. The pooled estimate for, again, this sample statistic is p-hat q-hat times the quantity 1 over n1 plus 1 over n2, all under the radical. Now, that's the SE for our formula. Okay, the formula for the test statistic then looks like this. Z equals, and it is p-hat 1 minus p-hat 2 minus the population proportion difference, which you believe to be 0. I never put the minus 0 in there, so usually the top of this formula for me is just p-hat 1 minus p-hat 2. Over the standard error, which we've just described as being a pooled standard error from both samples, so it's p-hat q-hat times 1 over n1 plus 1 over n2. Again, I want to make sure that we remember p-hat is the pooled success from both samples. Alright, the criteria that have to be met are very similar to what we've seen before. Trials must be binomial and random. The population must be significantly larger than the sample sizes, at least 10 times larger than N1 and 10 times larger than N2. And finally, the sample size. All NPs and NQs, that's weird, all NQs and NPs have to be greater than or equal to 5. So that's exactly what we said yesterday for the confidence interval on this same statistic. Let's see if we can't work one out here. Okay, we had a random sample of 600 probable voters. It says it was taken 3 weeks before the start of a campaign. And 321 of the voters said that they favored the new candidate over the one in office. But the week before the election, the new candidate had something revealed about him, which is unfortunately happening in our society a lot. Lots of unpaid parking tickets. Not a big deal. Subsequently, a new random sample of 750 probable voters showed that 382 favored the new candidate. We were above half here, we're less than half here. Okay? Actually, we're not. Both of those, I think, pretty close to half. And it says, does this data support the conclusion there was a decrease? Okay, that's something new for us. This one is actually asking if there was a decrease in voter support for the new candidate. Well, let's see. We want to take a look at our criteria. Random sample. So we've got the random and binomial because they either vote for the guy or not. Okay, that's one of our criteria. The probable voters in this area, so we don't know a lot about that. So the population, we're going to hope, right? We're going to assume that it's more than 7,500 people in this town, but we don't know. Sample sizes, however, we do know. N times p hat would be 321, and n times p hat 2 would be 382, both which are above 10. So our sample size is okay. We're going to go ahead and go with the test, even though we don't know for sure about the population size. We're going to assume, and if we were writing the AP test, this is what we would say. We're not sure about the population, but I'm going to go ahead with the test anyway. The null hypothesis is that the two proportions, before and later, are equal. The alternate hypothesis, this time they've asked us to consider a decrease in support. The way that I have it written, p hat 1 was the before and this is now. So I'm wondering if that means p hat 1 was bigger than p hat 2. Okay? P hat 2 would be the smaller of the two in my way of thinking. Okay? The two samples, this is deciphering what this means in terms of the context. The two sample proportions are the same or close to the same, and those proportions were in favor of this candidate for mayor. Let's go ahead and find the z for this, and before we do it, I might want to do some side work out here. P hat is the pooled, and so we're going to take the number of successes from the first sample, 321, add it to the number of successes from the second, 382, and put that over a sum of sample sizes. That's 600 in the first sample and 750 in the second. I'm going to go ahead and get my calculator up, and let's figure that. Alright, p hat in this context is right around, and I'm going to carry 4 digits here, 5207.5207. Of course, the more digits I carry, the more precise my answer. Okay, p hat 1 was 321 out of 600. We want the difference between that and p hat 2, which was 382 over 750. All of that over the standard error. Oh, and remember, you could be thinking that's the statistic minus what we expect, which is 0. I usually don't write that. Alright, here on our standard error, 5207 times the complement of that, .4793, multiplied by 1 over, and it's 600, 1/600th plus 1 over 750. Now that's going to be quite a chunk to put in the calculator, so I'm going to ask you to stop the tape and let's do that computation. Alright, I have a z-score of about 0.94. I need to know where my critical region is, which thinks I better get up here and find myself a significance. We use the alpha 0.05 since they didn't tell us what level of significance. We are doing a one-tailed test at the 0.5 level then. The critical value for z, the critical z at the 0.5 level, 1.645 if you're doing a one-tailed test. And our test statistic does not make it there. We have a 0.94. The p-value, that needs to be figured here, and that would be the probability that you get something larger than that 0.94 that we got. So I'm going to go to my z-table. Okay. I have my z-table, at least a piece of it showing, actually two pieces, and I wanted to just remind you, if we looked up positive 0.93, that's 0.90123, we come up with that value. Of course, that's showing what's below. We want the probability that you're above that. So we could subtract 1 minus 0.8238, but it's easier, folks, and still appropriate, since this thing is symmetric, to look in the negative 9.93. There's 0.123. 1762 is our p-value. 0.1762. Alright, now it's time for our judgment. We've got our criteria. Step 1, we have our null and alternate hypotheses. Step 2. Step 3, create this statistic. Now our judgment is coming, and we have two ways to say this. We did not fall in the critical region. We didn't land out in the shady. And our p-value is larger than alpha. We're testing at 0.5. So we must fail to reject here. Based on our sample, or on these samples, the proportion favoring this candidate did not change. Proportion of voters favoring this candidate is not significantly different. After the big reveal. Okay. After the revelation. Okay. He's getting about the same level of support. Okay, let's wrap up our lesson with a little true or false test here. It says that we're going to take two independent samples from two different populations that have the same proportions of successes. You repeat this millions of times and plot the distribution of the differences. First question, it's always the case that p hat 1 is equal to p hat 2. I don't think you can go there. Those samples could be they could have different proportions based on what we're sampling, even if the population proportions are true. Okay? It's true that p1 is equal to p2. Well, according to our statement up here, two different populations that have the same proportion of successes, yeah, I think you got to go with true there. Okay? That's what you assume to be true. Sometimes the difference between those proportions can be relatively large. That is also true, folks. You could get one sample that has a very much larger proportion of success than the other. The next one, theoretically, I'm going to underline that, the plot should be centered at 0. That is the truth. Okay? We assume, again, that those proportions are equal to each other. That means the difference between them is 0. And finally, to have a greater chance of having that difference close to 0, have larger sample sizes. 100%, folks. As we know, the larger the sample size, the more we zero in on the true population proportion. So that is the truth. All right, get out there and try that. You try. Have a good night.